Hey everybody, welcome back to physics. Today we're going to continue our discussion on waves. We're going to be discussing things like the speed of different types of waves and different terminology like period and frequency and what that means for our actual waves. But before we start, we're going to start with a quote. You guys know how much I love my quotes. Now this quote looks a bit different than the quotes I usually show in class. This is the famous quote by Neil Armstrong, but the quote is shown in the waveform of him actually speaking it. One small step for man, pause, one giant leap for mankind. The cool thing about looking at the waveform is it gives some different information than just looking at the quote itself. You can see where he pauses. You can see where the words are separated. You can see where he's louder at the higher amplitudes. You can see where he's quieter at the smaller amplitudes. Now this wave looks a little bit different than the waves that we've been looking at previously. This is what's known as a non-periodic wave. You can see the punches in his speech where we pause here. In order to better understand how these more complex waves work, we have to understand how the simpler waves work, like the periodic waves, where we have a nice smooth waveform. But it's pretty cool actually looking at the waveforms of these people actually speaking. Kind of gets you a little more information than just the words themselves. Okay, so when people speak, like I mentioned in this last video, the sound travels into your ear. This isn't a biology class, and you don't really need to know this, but I kind of wanted to discuss it for just a second. When Neil Armstrong speaks, or whoever speaks, that sound enters our ear. Now, it's pretty amazing that evolution gave us these really fine-tuned instruments in order for us to hear the world around us. This outer ear here acts like a funnel, getting all of the sound into our ear canal. So the sound comes in, and then the sound is vibrating the air around it. And by actually vibrating the air, we're vibrating our eardrum. The eardrum is just a thin membrane inside of our ear. And by vibrating the eardrum, we have this little connection of the smallest bones inside of your body. We have our hammer, anvil, and stirrup. By vibrating the eardrum, we change the sound wave into actually vibrating this membrane and these bones. The hammer, anvil, and stirrup start vibrating, and they start pounding into this little center area here. This is a fluid-filled sac known as the cochlea. And then by transferring that wave into the fluid-filled sac of the cochlea, we then transfer that into an electrical signal here, which goes into your brain. There's a few other cool things about the ear I'm not sure if you're aware of. Do you see these tubes here? These are what we call the semicircular tubes, and that's actually important for balance. Notice we have a tube going straight up and down, and we have a tube kind of going sideways. When you turn your head, the mechanism in your ear actually tells you whether or not you're balanced or where your orientation in space is, depending on how the fluid goes around your ear. This is called the Eustachian tube, and that has to do with regulating the pressure inside of your ear. But it's pretty amazing how we've evolved to have this mechanism in our head to understand the sounds in the world around us. Again, not something that you have to know for physics, but I think it's an important tie-in to see how our ears work and how we use it to interpret the world around us. All right, so let's get back to our discussion of waves. Last lesson we discussed things like amplitude, wavelength, things like that. But remember, waves are dynamic phenomena, meaning that waves are always changing. We can see the waves traveling through space. And if waves change with time, we can discuss characteristics known as the period and the frequency. Okay. So the period of the wave is the time it takes for one full wave cycle to complete, and that is measured in seconds. Now, the reason why I put this little animation on the board is because what the period is if I start my watch when the wave is here, we could time how long it takes to return back to that point, that same point in phase. So if we are looking at our watches, my watch over here, and we start 1, 2. This wave on the board has a period of about 2 seconds. That's how long it takes for the wave to complete one full cycle. Okay? So we're timing our waves, and that's important for us to know. Waves can take longer to complete one cycle, that would be a longer period, or they could take shorter to complete one cycle, that would be a shorter period. And period, we denote in our equations as capital T. T because it's a special amount of time, the time it takes to complete one full cycle. By extension, we could time how long it takes for a wave to complete, or we could see how many cycles the wave completes in 1 second. And this is what we call the frequency. The reason why we call it frequency is quite literally we're seeing how frequent the wave is, right? How frequently it occurs. The number of cycles or oscillations the wave completes in 1 second, measured in cycles per second. And in physics, we denote cycles per second. We use the word Hertz for that, which is Hz. It's named after a German physicist, Heinrich Hertz. So waves that have a lower frequency have a longer period, right? The lower the frequency means that it takes longer for the wave to complete that one full cycle. It's going to do less cycles every single second. But as we increase the frequency, you can see that this wave repeats very frequently, right? So it's going through more cycles every second. And something I kind of wanted to show you here, we can model our waves. I'm sure you've seen it in math, but we can model our waves using trigonometric functions, these periodic functions. This is a normal sine x wave. By increasing the frequency, we're increasing that number that we're multiplying the argument by. Not something you have to know for physics, but a good extension for math. The higher the frequency, the more the waves are going to repeat themselves every second. So you might be thinking to yourself, you could kind of see the relationship between period and frequency, right? If period is seconds per cycle, how long it takes for one cycle to complete, and frequency is cycles per second, how many cycles we go through every second, we could kind of start to see a mathematical relationship between the two. Frequency and period are related. Like I said, period is seconds per cycle, right? How long it takes for one cycle to complete. We measure period in seconds. And frequency is defined as cycles per second, which is how many waves go through every second. They're multiplicative inverses of each other. If you know one, you can calculate the other using this equation. The period capital T is equal to 1 over the frequency. Frequency is measured in hertz. And just take a look at the units. We have seconds here, and frequency is measured in cycles per second, 1 over seconds. 1 over seconds, the units work out. Dimensional analysis works here. So frequency is pretty important when it comes to waves. You might have heard of like hertz be thrown around in your everyday life, right? If you're tuning into your radio, like I talked about last video, you're actually tuning into the frequency of the electromagnetic wave so you could hear the signal. And those frequencies are in megahertz. Megahertz, mega, that prefix mega is millions of hertz. So 102.3, you're tuning into it. You're tuning into 102.3 megahertz for the electromagnetic signal there. Some other things like your Wi-Fi router tends to work on like 2.3, something like that, about 2 gigahertz. And that giga means billions of cycles per second, right? 2.3 billion cycles per second. That's what your computer looks for when it's trying to tune into your Wi-Fi router. And not only that, but the extension for things like music. For those of you who are musically inclined, if you hear a sound wave that has a frequency of 440 hertz, 440 hertz means the air is vibrating at 440 cycles per second. That number is important. 440 cycles per second, that would be middle A. And you can play that note on a bunch of different types of instruments. So the notes for our music, the frequency of our radios and our routers, they all depend on this idea of period and frequency. So now that we saw that waves take a certain amount of time for them to complete one cycle, and we looked last lesson at things like the wavelength, how much space these waves take up. And I'm sure you've seen, like, if you have a slinky in your hand and you wiggle the slinky, or if you tap the water, you can see the wave pulse move along that medium. Putting all these things together, we know that waves travel at a certain speed, that energy is transferred at a certain speed. We can see the pulse move through the slinky. We can see how long the pulse, how far the pulse moves, and over how much time the pulse moves. So we can actually calculate how fast these waves move through our world. And we can do that using this equation here. V is equal to F lambda. My TV's hot. I don't know why. V is equal to F lambda. So the speed of the wave measured in meters per second. Speed is always measured in meters per second. That's how fast the wave is moving through our universe. Speed of the wave is equal to the frequency multiplied by the wavelength. And the wavelength is something we talked about last lesson. It's quite literally the length of the wave. If I put a meter stick across the wave, I can see how much space it takes up to, until it repeats itself, right? The distance between any 2 points in phase. And there's a lot of different types of waves in our world, like we discussed. We have our electromagnetic waves, we have our mechanical waves, and then mechanical waves can split up into sound, slinky, water waves. For now, I want to discuss sound waves and light waves, and the difference between the speeds of these two types of waves. You can calculate the speed of any type of wave using this equation, but let's focus here on sound and light and what affects their speed throughout the universe. Let's start with sound. Sounds move at different speed depending on the properties of the material it moves through. The speed of sound at STP, and if you remember from chemistry, STP stands for standard temperature and pressure, and that speed is about 331 meters per second, which is pretty quick. If you remember, that meter is about 3 feet. We're moving at about 1,000 feet per second when it comes to sound. This important number can be found on the reference table, page 1. Now that's the speed of sound at STP. Now what if I change the temperature of the air? If we increase the temperature of the air, that increases the speed of sound through the air by about 0.6 meters per second. That's for every 1 degree Celsius increase in temperature. Now, believe it or not, sound can actually move through liquids and it can move through solids. In liquids, sound travels faster than in air. In air, we have a diffuse grouping of particles. And so in air, it actually moves slower than in liquid. In liquid, it moves faster because those particles are grouped closer together. So those particles can affect each other a little bit more. Sound actually moves about 4 times faster in water than it does in air. Sound can also travel through solids, and it travels even faster than in liquids because those molecules are grouped even closer together. Sound travels about 15 times faster in steel than it does in air. So that's some properties of sound. If we change the properties of the medium that the mechanical wave moves through, we change the speed at which that wave moves. So this is pretty fast, about 1,000 feet per second. But how does that compare to light? For light, for all electromagnetic waves, they move the fastest in a vacuum where there's nothing in the way, no medium in the way. And light, all electromagnetic waves, travel at about 300 million meters per second. That's about 900 million feet per second. And light is the absolute fastest thing in the universe. It's our universal speed limit. Nothing can go faster than the speed of light. And these electromagnetic waves slow down when they travel through a medium. So if we send that light out of a vacuum into air, water, glass, anything like that, they actually do slow down. But light travels very, very quickly. But it has a finite speed. The light doesn't travel instantaneously through our universe. When you flip on the lights in your room, the light seems to instantly fill the room. But it does take a certain amount of time for that light to completely fill the room. We talked about in class that when you look at the sun, The light from the sun takes about 8 minutes to go from the surface of the sun traveling into your eyes. So whenever you look up at the sun on a, sunny day, make sure you're wearing sunglasses. Don't look at the sun. But if you're looking at the sun, you're not seeing the sun as it is, you're seeing the sun as it was 8 minutes ago. And when you look out at the stars out in the sky, like a clear night sky, you're seeing the stars not as they are now, but as they were when the light left the star. So a star that is, let's say, 100 light years away, that means you're seeing the sun as it was 100 years ago. When you look out in space, you're quite literally looking back in time. Light is the fastest thing in the universe, and it's very, very quick, but it does take some time to move. Okay, so we could use this relationship between sound and light to help us understand the world around us. So if you're standing here and you see a lightning strike, light travels at about 1,000,000 times faster than the speed of sound. So we could use that relationship to see how far away the lightning storm actually is from you. So next time you're in a lightning storm, see the lightning strike and then count the seconds between from when you see the lightning strike to when you actually hear the thunderclap. And that amount of time could tell you how far away the lightning is from you. And you could use this relationship here to see how many miles away the lightning storm is from you. So count the seconds, divide the seconds by 5, and then that'll tell you the distance the lightning is away from you in miles. It's pretty cool. And connecting to that video that I sent you yesterday, that's why when you're in the nosebleeds of a stadium, you could see the batter hit the ball before you actually hear the crack of the bat. There's a difference between how fast that light reaches your eyes and how fast the sound reaches our ear. So, I would like for us to try some examples using some of the ideas that we discussed so far. Remember, the big idea here is that period is how long it takes for a wave to complete one cycle. Frequency is how many cycles it goes through every second. And we can calculate the speed of the wave using V, the speed, is equal to F, the frequency, multiplied by lambda, the wavelength. So we have this wave up on the board here. And what's given is that this is a periodic wave traveling through a uniform medium. The frequency of the wave is 2 hertz. I'm going to write on my TV again. So the frequency of the wave is equal to 2 hertz. Okay? And remember what hertz means. That means it goes through 2 cycles every single second. Also notice on the diagram that it's giving us the distance between here and here, which is about 6 meters. Based on the given information, we want to find the period of the wave and the speed of the wave. So let's start with the period. If you look on a reference table, the period t is equal to 1 over the frequency. The frequency was given to be 2 hertz. So we can calculate the period. T is equal to 1 over 2 hertz. So 1 over 2, that is equal to a half. 0.5, period, is measured in seconds. That's how long it takes for one wave to complete. Period is equal to 0.5 seconds. It takes half a second for this wave to go through one complete cycle. All right, but what about the speed of the wave? Gonna erase. So the speed of the wave, we can use our relationship that we just learned. V is equal to F times lambda. This is in page 5 of the reference table. That's where all of the wave relationships are. Okay, well, our goal is to find the speed. We have the frequency. Do we know the wavelength? Be very careful here. What is wavelength? Wavelength is the distance between any 2 points in phase. They tell us that this distance is 6 meters, but these 2 points are not in phase. So what's our wavelength? Well, a wavelength would be from here to here, because those 2 points are in phase. So this distance of 6 meters goes through 1.5 cycles. This would be 2 cycles over here. There's 1.5 cycles. So that means this one wavelength is 2/3 of the way to the total of 6 meters. So doing some math quick in our head, if this is 2/3 of 6 meters, 2/3 of 6, this would be 2, 4, 6. 2, 4, 6. So that our wavelength is equal to 4 meters. Okay? And now we could use that to calculate the speed of the wave. V is what we want. Frequency is 2 hertz. Lambda is equal to 4 meters. 4 meters times 2 hertz is equal to 8 meters per second. Perfect. Now you might be asking, how come meters times hertz is equal to meters per second? Remember that hertz is equal to 1/seconds. Cycles per second. We're counting how many cycles there are every second. Meters multiplied by 1/seconds ends up being equal to meters per second. So the period is 1/2 second. The speed of this particular wave is 8 meters per second. All right, last question I'd like us to try. At an outdoor physics demonstration, a delay of 1/2 second was observed between the time sound waves left a loudspeaker and the time that these sound waves reached a student through the air. 1/2 second is a pretty long time. Just like when we're in the baseball game, we can measure about 1/2 second from when the wave left the speaker to when it reached the observer's ears. If the air is at STP, standard temperature and pressure, how far was the student from the speaker? Well, we know it took 1/2 second to get there. How fast was this wave moving, this sound wave? Well, at standard temperature pressure, we can look at our reference table, page 1, and we know that the speed of sound in air is equal to 331 meters per second. We also know that the time it took to reach the student was 1/2 second. How can we use that to figure out how far the student was from the speaker? Well, yes, we're looking at waves here, right? But don't we know a relationship between speed and time? This wave is moving through the air at standard temperature pressure. The speed doesn't change. There's no acceleration. If there's no acceleration, speed is simply equal to distance over time. It doesn't matter what's moving, whether it's an object or if it's a wave. This relationship holds as long as the speed doesn't change. The speed of anything is equal to the distance it travels over the time it took to get there. We can use this relationship to figure out the distance. Well, the speed is equal to 331 meters per second. We want the distance. The time was 1/2 second. That's how long it took to get there. We can use that to find the distance. 331 times 1/2 should be equal to 165.5 meters. And that's the distance from the loudspeaker, is the boombox, to the student, which is over here. Okay? Now this is like a kinematics equation, right? This is actually the first physics equation we learned this year in physics. The distance from here to here, if we know it took 1/2 second to get there, and we know how fast the thing is moving, we can easily find the distance. So you can use those early equations to help us out here when we're looking at waves. Be very careful for these types of questions. Okay, so this is the answer, 165.5. I'm going to erase. I've seen questions before. For example, I've seen this type of question where we have a boat. There's our boat. and they sent a sonar signal. Sonar is just sound. They sent a signal to the bottom of the ocean, right? And then they heard the signal back a certain time later. Well, if they heard the signal back, that means it traveled and hit the ocean floor and then traveled back to the boat. So that would be double the distance to the ocean floor. So just be careful with these types of questions and what they're asking us. Now, at the end of this lesson, we better understand the concepts of frequency, period, and how these waves are dynamic. They change. They take some time to complete their cycle, and they go through certain amounts of cycles every second. And they have a finite amount of speed for how fast they move through the universe. All right. So that is it for our lesson today. I hope everyone's doing well, and I'll see you in the next video.